into some real organic molecules. We're going to deal here with organic compounds, and we're going to talk more about the concept of functional groups. Now, we mentioned functional groups way back in chapter 1. We said that when we hybridize the electron cloud around carbons, that we can form tetrahedral geometry. We refer to that as sp cubed. And we say that these are all single bonds or single bonds. When we have trigonal geometry, 120-degree angles, we form that using 1s and 2p orbitals. This is sp squared hybridization. We call this a double bond. One of those is a true sigma bond, and the other is a pi bond formed from the leftover p orbitals. When we do reactions of alkenes, we will see that the reactions always occur around this double bond because it's a very good source of electrons. If we take 1s and 1p as p hybridization, we get a triple bond. One of those is sigma, and two of them are pi bonds. Now, at the time, we said that these represented functional groups. Functional groups here, these are alkanes, alkenes, and alkynes. We're going to go through the whole list of functional groups, or part of it anyway. There's a lot of stuff to digest here, so don't get overwhelmed with it. But the important thing about functional group chemistry in organic is that virtually all alkenes, regardless what else is attached, will undergo the same classes of reactions. So you really don't need to focus so much on the entire molecule. You simply look and say, it's got a double bond, it's going to do this. It's going to add bromine to form a 1,2-dibromide, and the stereochemistry will be trans. That's the kind of stuff you'll say. So let's go ahead and look at functional groups. Carbon-carbon double bond is an alkene. If we have an OH group, we talked about this, we'll call this an alcohol. If we go and put an oxygen in the middle between two carbons, we form what's known as an ether. Now, once again, the advantage of doing the functional group thing is that everything with a double bond is going to react in a very similar way. Everything with an OH is going to react in a similar way. If you have an ether, they are so unreactive that almost nothing happens to them, regardless of what other things are attached. So that's the beauty of functional group description. Let's go back to our alkene, the example that I said. If we have an alkene like this, again, it doesn't really matter what's attached out here. And you put this in the presence of something like bromine, Br2, usually in a solvent. You will react at the double bond to form a 1,2-dibromide. All alkenes will do this. The stereochemistry is always with bromines on opposite sides of the molecule. And the mechanism is always stepwise. We have what's known as a bromonium ion intermediate. So when we do alkene reactions, again, it doesn't matter what's attached to the functional group. They're all basically going to do this thing. It makes organic chemistry doable because there are just so many compounds and so many reactions. All right, here's our list. Again, this is going to be a little overwhelming, especially since you don't have the handout. So, again, I have to apologize. Alkane. If we have only sp cubed carbons, this is going to be called an alkane. They're all single bonds. An example is our 2-carbon hydrocarbon here. We will call this ethane. We just saw an alkene. Anything with a carbon-carbon double bond will be an alkene. An example, here's our 2-carbon alkene. This is ethene. Alkyne is our triple bond. This is ethyne. It's also referred to commonly as acetylene. If we have double bonds in a ring, that's a different functional group. These don't react the ways other double bonds do. When you get to benzene, I believe in chapter 13 or 14, that was the one thing that was so difficult to understand. It's a resonance phenomenon. This is referred to as an air ring. Abbreviation is simply AR to represent the benzene ring. And you can, of course, attach things to it. Halides. We can remove a hydrogen and we can stick a halogen on. An example here is this guy, 1 carbon, we will call this bromomethane. We've seen alcohols. Again, we're simply going to attach the OH group. This is methanol. We saw an ether. Ethers are notoriously unreactive. This is dimethyl ether. We can take a hydrogen off, put a nitrogen on. We get the functional group that's called an amine. Remember, just like all nitrogen compounds, there's a lone pair of electrons here. And that's where all of the chemistry resides in amines. Carbon-nitrogen triple bond is called a nitrile. This is called acetonitrile or methanitrile. This is a pi system, just like we had for triple bonds, and this can undergo many of the reactions of other triple bonds. We also have a lone pair of electrons here on the nitrogen. A couple more. We can put a nitro group on the end, nitromethane. This is called thiols. Thiols stink. The essence of skunk is butane thiol. SH is very similar in its chemistry to the OH, except they stink. Really bad. Sulfides do also. Here's a sulfur. This is the sulfur analog of an ether. Now those are the basic, simple functional groups. Probably the ones that are certainly very important in 235 are groups that feature a carbon-oxygen double bond. We will call those carbonyl compounds. CO double bond is a carbonyl. We will name these depending upon what's attached on either side of our carbonyl. Simple rule, if we have a hydrogen, that's called an aldehyde. If we have 2 carbons, it's called a ketone. If you have an OH, as we saw, that's a carboxylic acid. If we have an O carbon attached on this side, carbon on this, that's called an ester. Esters are derivatives of carboxylic acid. Instead of the hydrogen, we simply have a carbon. We can put a nitrogen there and make it an amide. Amides are very important because this amide linkage is the same linkage that occurs in proteins. So that's the amide bond, just the nitrogen attached to one side of our carbonyl. We could put a halogen on, make it an acid halide, or put another whole carboxylic acid on this side and call it an anhydride. Now again, this list will make you nuts. We will look at these things and deal with them one by one as we go through the functional groups. Each of these will have unique reactivity. And I keep saying it, but that's the one thing that makes organic chemistry work. We can simply classify all of these things by their functional group reactions. All right, we dealt with representation of carbon compounds for a little bit in the first part of chapter 2. We said that because of the dynamic nature around carbon-carbon single bonds, that there really is no one right way to draw it. All of these are undergoing lots and lots of flips and flops and various interactions, etc. So if we were to draw this 5-carbon thing, it really doesn't matter if we draw it, as a zigzag or if we bend it up or whatever. This is an example of what's known as isomerism. Organic chemistry is going to be full of isomerism. This is conformational isomerism. And because we have free rotation around all these single bonds, this thing basically exists at equilibrium in all possible orientations. Now that means, again, as far as you're concerned, if I ask you to draw this particular hydrocarbon, you could draw it darn near any way you want. As long as you have a chain of 1, 2, 3, 4, 5 carbons, and here on carbon number 3, you have a 2-carbon chain. It doesn't matter how you draw it. Also on the drawing palette, it doesn't matter how you draw the thing either, the smile string always turns out the same. So that's kind of neat. Because these things interconvert so rapidly, roughly 10 to the 6 times per second, conformational isomers are not considered to be separable, and they're all regarded as identical forms. All right. This is just an example here. This is a 5-carbon chain with a 1-carbon side chain here at carbon number 3. And we can draw this as our chain like that. That's an acceptable thing. Here I've rotated this down a bit. More traditional zigzag. Here I've bent it back on itself. This is our longest carbon chain. Now, when we go to name simple and branched hydrocarbons, the first thing that you want to do is to look at the structure that you're trying to name and come up with the longest continuous chain of carbon atoms. This is the notion of nomenclature. If we look at this, we have a 1, 2, 3, 4, 5 carbon chain and a 2-carbon side chain, don't we? This has a formula of C7 and H16. If we look over at this guy, we have 1, 2, 3, 4, 5, 6 carbons in our longest chain, and we have a 1 carbon side chain. Nonetheless, if we did the formula, this is still C7H16. These are different chemical compounds. These are referred to as constitutional isomers. Constitutional isomer will have the same molecular formula, so it has the same number and types of atoms, but they're simply arranged differently. With this guy, our longest chain here is 1, 2, 3, 4, 5. So when we go to name it, we will name it based on the 5 carbons. This guy, our longest chain, is 6, and we would name it based on the 6 carbon parent chain. Conformational isomers, you don't have to worry about so much. Constitutional isomers are real. These are totally different chemical compounds. Any questions? All right. There's a fun game that you can play. It's called Write the Constitutional Isomers. So why don't you sit down and see how many proper carbon compounds you can draw having a molecular formula C3H8. Now what you want to do is start off with a chain of 3 carbons, place 8 hydrogens around it, and see if there are how many ways you can arrange these. Well, this one is actually really, really simple, because there's only one way to do it. 3 carbons in a row, that's the only thing you can do. Our chain here, this is our parent. There's no other way to arrange and still get C3H8. All right, let's make it a little more interesting. Do C3H6. So again, start with 3 carbons. Now we only have 6 hydrogens. Turns out that there are 2 ways to do this. The simplest is to do this, 3 carbons. Because we only have 6 hydrogens, we need to have a carbon-carbon double bond. So 1, 2, 3, 4, 5, 6. Doesn't matter if the bond is here instead of here, same compound, because remember, they're flipping around. But there's another way. There's another compound. Anyone have it?
Is it just a triangle?
Yep. We can take them and simply make a triangle out of it. Again, 3 carbons, 2, 4, 6 hydrogens. We will see when we do alkenes that this is called a degree of unsaturation. It, from the formula, tells you how many double bonds or rings you have in your structure. that says 1 degree of unsaturation, so 1 double bond or 1 ring. Let's do another one. Do C4H8. See how many of these you can come up with. Should be able to make 5. We're going to have to put in double bonds or rings. The simple default method would be to put 4 carbons in a row and stick a double bond in it. Now we could do it at the end carbons or we could do it in the middle. The full set looks like this. Again, 4 in a row, put a double bond here, or put the double bond here. We could also have a 3 carbon parent with a 1 carbon side chain. We can put 4 carbons in a square. Or we can go back to our triangle and just have a 1 carbon side chain. All right, well, we can do this with heteroatoms as well. Do C2H6O. You should be able to come up with 2. Well, we can either put the oxygen on the end. It's got to be a 2 carbon chain, right? Make a 2 carbon chain with an OH on the end, or put the oxygen in the middle. Simple alcohol or an ether. All right, well, these guys were really, really simple, right? No fun putting those on an exam. So let's just make it just a little more complicated. Instead of C2H6O, let's do C3H6O2. That's a good example. So we've increased our carbons by 1 and our oxygens by 1. Remember, every oxygen must have 2 bonds to something. Every carbon must have 4. And we're obviously going to need double bonds and rings. Well, we have just done a minor change in our formula here, right? But the results are dramatic. These are all constitutional isomers of C3H6O2. Here we have a carboxylate ester. This is an aldehyde and an ether. Another aldehyde, and an alcohol. These are both ethers. But this isn't just it. These are also And the whole point of this, no, this isn't a good test question. The whole point of this is just to demonstrate how complex carbon compounds can get as we start adding heteroatoms and making double bonds and things like that. All of these and all of those on the previous slide. So these guys and these guys, these are all constitutional isomers. All right, there's another game that's fun to play. And that is, are these guys the same or are they different? Are they identical compounds or are they constitutional isomers? Remember, we're not interested in conformational, only constitutional. Now, what you really just have to do here is be able to look at our various structural representations and compare them. The really hard way is to sit and count up all your hydrogens and all your carbons, come up with a formula. But you can do that. This is C5, 1, 2, 3, 4, 5, and there are 12 hydrogens. With this guy drawn in a line drawing, we have 1, 2, 3, 4, 5, 6 carbons and 14 hydrogens. So these two guys are totally different compounds and they are not isomers. All right, you ready for another one? Look at these two. Are they identical? Are they constitutional isomers? Or are they totally different compounds and not isomers? Well, our first one here requires you to read a condensed formula, doesn't it? Remember, the first thing you want to do is to trace out your carbon chain. So we have 1, 2, 3, 4, 5, 6 carbons in our chain. Over here we have 1, 2, 3, 4, 5, 6 carbons in our chain. That's good so far. With this one, we have a chlorine bonded here to our third carbon, and a chlorine here bonded to our second carbon. If we started numbering down here, we would have a carbon bonded to our third carbon, and from this end, a chlorine bonded to our second carbon. 6 carbon main chain, chlorines in positions 2 and 4. 1, 2, 3, 4. 6 carbon chain, chlorines in positions 1, 2, 3, 4. These are identical compounds. How about these two? Trace out your carbon chains. Here we have 1, 2, 3, 4 carbons in a chain and a CH3 dangling off. This is C5H10. Now, even though this looks similar, remember these guys are CH3 groups, aren't they? And these are just hydrogens. Therefore, this is C7H14. These are clearly different chemical compounds, and they're not isomeric.
Why are those CH?
Remember, anytime you have a line drawing, if it goes up and just ends in space, that's a CH3. Triple bond here. In our first representation, we have carbon-carbon triple bond, a CH2 attached to a chlorine. 3-carbon main chain, chlorine in position number 1, carbon number 1 here. And we have a triple bond. Now, when I drew this, did I have to stick this hydrogen on? I couldn't leave it off totally, because that would be a CH3, wouldn't it? But it's acceptable to do this just to show that there is a hydrogen there. Or you could just leave it off totally, just show the triple bond. All right, here we have a carbon-carbon triple bond. These are hydrogen, a CH2 and chlorine. 3-carbon main, chlorine in position 1. And yes, they are identical. Let's do one more and then we'll get to the real test question. Carbon-oxygen double bond, that's a carbonyl, remember? Bonded on one side to a nitrogen, that makes it an amide. In this guy, we have our amide. Nitrogen is bonded to a hydrogen and a CH3. Here we have a 2-carbon chain with a 1-carbon side chain. C5H11NO. This is referred to as an N-methyl. That's our CH3 group, amide. Over here, we have a nitrogen with a hydrogen and a CH3. We have our carbonyl. But here we have 1, 2, 3 carbons in a straight chain, and here we were branched. It's also C5H11NO. It's also an N-methyl amide. However, they are clearly different compounds. This has a 3-carbon main. This has a 4-carbon main. These are constitutional isomers.
So if the last one on the right was on the bottom, then they would be
Yep, if
identical.
the branch was here, they would be identical. All right, now I kind of fooled around a little bit before, and I said that draw the isomer question was on an exam, but it wasn't, of course. Terrible question. But in fact, this one was. Are these two constitutional isomers different chemical compounds or identical? Well, they're not identical, that's for sure. And once again, the point here is to show the diversity of carbon compounds. Here we have double bonds and a triple bond, Here we have what we will call a polycyclic compound. That means many rings. All right. Let's start off by simply doing a formula. I mean, how would you approach this? First thing I would do is count up how many carbons I have, how many hydrogens. For this guy, let's just start somewhere and number. Doesn't matter how you number it. Yeah, it does. But right now it doesn't. But if you trace this around, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons. All right? How about this guy? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 carbons. Let's go back to this guy. How many hydrogens are on here? Remember, every vertex represents a CH2. Every truncated line would be a CH3. Well, there are no CH3s here. These guys are all going to be CH2s, right? Here we have 3 bonds to carbons, so this has to be a CH. If I sprout all my hydrogens, it would look like this. There's our 2 CH2s, and all the rest of these are just CHs. So if we count them all up, we get C12H14. Now, we've already said the one on the bottom here is 12 carbons, doesn't it? Before I say, count the hydrogens. We'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We didn't draw it, but we know it's here, right? That's 14. They are both C12H14. Therefore, since they are certainly not the same compound, they are constitutional isomers. Now, isn't that a fun problem? That's a fun problem. All right. Let's go ahead and move into how we name simple compounds. We're not going to be able to name these guys yet. Eventually, you would, but not now. Let's just start off with simple hydrocarbons and simple branched hydrocarbons. These are the functional group alkane. Remember? All single bonds. First thing you want to do is to find your longest chain. And your name is simply going to be based on the number of carbons in that chain. We're dealing with alkanes. So after we count the number of carbons, we're going to end our name by adding A and E. A and E tells us it's an alkane. Now, when you count in organic chemistry, you're going to do it this way. 1 carbon is a meth. 2 carbons is F. 3 is prop, bute, pent, hex, hept, oct, non, dec, and then it gets stupid. But you should know the first 10, okay? Because all of these are alkanes, we take our prefix, that's meth, and add A and E. We have 5 carbons, our prefix is pent, and we add A and E, pentane. We have 10 carbons in a row, our prefix is dec, and we add A and E. So for simple hydrocarbons like that, it's very, very simple, okay? The next thing we have to think about are side chains. Because remember, many of the examples had a parent chain with things dangling on. We're going to name these, again, based on the number of carbons in our side chain. We will call these alkyl groups. An alkyl group is formed by removing the hydrogen from the parent chain and sticking it on somewhere else. We will often abbreviate this as R, for radical, to show it's something. It's a carbon chain. And we will name our alkyl group by taking the number of carbons in it. We're going to remove the A and E and put a YL. So here we have 1 carbon. That would be a meth, right? Because it's going to be attached to something else, we will call this a methyl. If we had 2 carbons, it would be an F. We add it to some other chain, and that makes it an ethyl. F tells us there are 2 carbons. YL tells us it's attached to somebody else's chain. This is methane, 1 carbon, 4 hydrogens. Yank hydrogen off to attach it to something else. We will call this a methyl. 1 carbon attached to somebody else's main chain. Example, if we had an alcohol, we have this group, which is our methyl, attached to the alcohol. We would call that methyl alcohol or methanol. Here we have a nitrogen attached to our carbon. Looks like this. This is an amine, and we would call it methyl amine. Now we'll do nomenclature for each of the functional groups as we come to them. But it's all going to be based on these very simple rules. Any questions? Once again, here's the alkane version, 1 carbon, methane. Here's the alkyl group, and it's known as a methyl. 2 carbons, ethane, 2 carbon side chain, ethyl. 3 prop, propyl. Bute is 4, butyl, and pent, pentyl. Now just to make organic chemistry impossible, because it's a very old science, things weren't always quite disorganized. And so people kind of named these things anything they wanted to. Instead of a 5 carbon chain properly being called pentyl, it will also be called an amyl group. Now I will never do that, but you will see amyl alcohol, isoamyl alcohol, sec-amyl alcohol, etc. It'll make you nuts. Designed to. We can refer to those as trivial names or common names. But in this course, we're going to stick to systematic. There's also a nomenclature that's important to know, because we're going to deal with this a lot when we're dealing with intermediates in alkene reactions. And that is, it's a very simple concept. We will refer to a carbon as primary, secondary, tertiary, whatever, based on the number of other carbons it's attached. So again, it's a simple concept. If we have one carbon attached to one other carbon, that's primary, often shown as 1 degree. If our carbon is attached to 2 carbons, that's secondary, 3 carbons, tertiary, and if we have a carbon in the middle of 4, that's a quaternary carbon. Simple nomenclature, but just make sure that you understand what we're talking about. Let's go ahead and just do a quick one. Look at this guy. Pick out primary, secondary, tertiary, and whatever. Which one? Oh, this is a secondary carbon. Again, no, tertiary carbon. 1, 2, 3. These guys are primary carbons. They're attached only to one other carbon. This guy will be a secondary carbon attached to 2 other carbons. And this guy here, the red one, is a tertiary because it's attached to 3 carbons. Simple nomenclature, simple concept, but we will use these terms over and over again. Any questions? All right, let's do some rules. These are called the IUPAC rules, International Union of Pure and Applied Chemistry. These, you refer to these as IUPAC names. That's their official name. The first rule, when you're looking at a simple branched hydrocarbon, we want to pick out the longest continuous chain of carbon atoms. In our first one here, very simple, this would be 1, 2, 3, 4, 5, 6 carbons. Our second one here, we might be tempted to go this way, but of course that's wrong. Our longest chain would be 1, 2, 3, 4, 5, 6 carbons. And finally over here, our longest chain would be 1, 2, 3, 4, 5, 6, 7 carbons. So step 1, you look at your molecule and you pick out the longest chain. For this one, very simply, we have 1, 2, 3, 4, 5, 6 carbons in a row. This one, we're going to start up here and go this way. And for this guy, we're going to start at either end here, but have to include our 3 carbon side chain here. So it looks like that. So step 1, you find your longest continuous chain. Everyone happy with that one? Second rule. We're going to number this parent chain. And we're going to number it beginning at the end closest to the first substituent. Now, for substituent, in this case, we're talking side chain. We are then going to number in such a way that for all of our substituents, we're going to get the lowest number sequence at the first point of difference. And finally, if we have a tie for parent chain, we're going to choose the parent chain with the greatest number of substituents. So those are the three things we're looking for here. We're going to find our parent. We're going to number it so that we can get our first substituent, the lowest number. And if we have a tie, we're going to do greatest number of substituents. So look at this guy. Very quickly, I know you don't have this, but copy it down. And come up with the longest chain. Well, we could have 1, 2, 3, 4, 5, 6, 7 carbons in a row. Right? That work for you? We could also start up here and have that with 1, 2, 3, 4, 5, 6, 7 carbons in a row. Those two are identical, right? Now we want to take these and we want to number them. Our rule says we want our lowest number sequence at the first point of difference. If we started numbering out here, our first substituent would be at carbon 1, 2, 3, 4. If we start numbering here, our first substituent is carbon 2. How about this guy? We had drawn it this way before. What if I took that as my longest chain? Does that work? It has 1, 2, 3, 4, 5, 6, 7 carbons. This one violates our third rule here. Greatest number of substituents. Here we would have 2 side chains. Here we only have 1. So that's a knot. As I said, we're going to start numbering here so that we wind up with a substituent in carbon 2. Our next substituent is carbon 4. If we use this chain, we would have only 1 substituent, and it would be attached to carbon 4. So this is what we want. Are you happy with that? All right. Once you identify the main chain, once you identify how to number the chain, you want to look at the number of substituents that you have. If you have more than 1, we are going to indicate how many using di, tri, tetra, etc. So far you know your parent chain. You know the numbering on your parent chain. Now we're going to do all of our substituents, say how many there are using a multiplier. We are going to write this name now as a single word. We will use dashes, hyphens, and prefixes and commas to separate our numbers. So go ahead and copy this thing down. Decide on what the main chain should be. Largest chain with the greatest number of substituents. If we started up here, we would have 1, 2, 3, 4, 5, 6, 7, 8, right? If we started here, we would have 1, 2, 3, 4, 5, 6, 7, 8. They're both octanes, aren't they? If we went this way, we would have 1, 2 side chains. If we go this way, we have 1, 2, 3, 4 side chains, or yeah, 4 side chains. So that's better. So our parent chain here should look something like this. Now we're going to number it beginning at the end closest to our first substituent. So this is going to be carbon 1. So we have methyl groups here in carbon 2. In carbon 1, 2, 3, 4, we have a 3-carbon side chain. You remember what that is? It's a propyl, right? And over here we have another methyl in carbon 6. So, we have 3 methyls, we'll call that a trimethyl, and we have a propyl. When we go to write this name, we're going to arrange the substituents alphabetically, but we're going to ignore the multiplier we put on. We're going to indicate where the methyl groups are here using numbers and commas. So 2, 2, 6, and this is a 4 propyl. Go ahead and write the name. Methyl comes before propyl, right? So we're going to start off by saying it's a 2,2,6 trimethyl. We're going to put a dash in. Say 4 propyl. Then we're going to say our parent is simply an octane. 2,2,6 trimethyl, 4 propyl, octane. You'll note, this is all one word, only dashes and commas, no spaces. There is yet another rule. Oh, I said not 3 3s, but 3 7 7 trimethyl. If we started numbering here, then this would be carbon 3, wouldn't it? This number sequence, 2 2 6, is better than 3 7 7. So we want to start here to get our lowest number sequence. Now, what happens if you have a side chain, and that side chain has a side chain? We've already seen that carbon compounds can get very, very complicated. Go ahead and look at this and figure out your longest chain. Longest chain is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we did this, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So our longest chain is going this way. We're going to start carbon 1 here so that we have our first substituent at carbon 2. Now we have 2 methyl groups here, don't we? So we know it's going to be a 2,3-dimethyl. But what do we do with this thing? The rule says we are going to number this separately, starting at the point of attachment. Now this is a 3-carbon side chain, isn't it? So it's a propyl. But it's a propyl group with a methyl step on it. This must be carbon 1, because that's the point of attachment. So what we have to say is, attached to our decane, we have a 3-carbon side chain, so that's a propyl. And in carbon 2 of our propyl, that's this guy, we have another methyl. So this is a 2-methyl propyl. The 2-methyl propyl is stuck on carbon 6 of our parent. So these are our side chains. Go ahead and write the full name. You'll note that I have put the 2-methyl-propyl in parentheses. It is a propyl chain with a methyl group in carbon 2 attached to carbon 6. Okay, sorry, I just had to do something. All right, so our parent is going to be a decane. We are going to have 2,3-dimethyl. Ignore the di, and we have a methyl propyl. Methyl come before methyl propyl alphabetically. Again, we string it all together, one word, decane at the end, only dashes and commas, no spaces. Any questions? Now, just to make this all more interesting, this 3-carbon side chain is legally a 2-methyl-propyl, right? It's also called an isopropyl. You've heard of isopropyl alcohol, right? Well, that's actually 2-methyl-propyl alcohol. These are common names. Again, they will make you nuts. I will not use them. I will try my best to keep it IUPAC, but you will see them everywhere. Isopropyl, isobutyl, that's 4-carbon total. This is called sec-butyl for secondary butyl. This is tert-butyl because we have a tertiary carbon. Very, very common names. Again, they will make you nuts. If we named this using this, it would be an isobutyl. Again, it just makes you crazy. But this is the one that we want, and that's the one that you want to do on exams and whatever. Finally, if we have things like halogens attached, we're going to treat those just like any other side chain. They will have the same priority as a carbon side chain, and you would just go ahead and name it as a chloro, fluoro, bromo, whatever substituent. In this molecule, we have an 8-carbon parent. We have methyl groups, 2 of them, in carbon 2. We have a propyl group in carbon 1, 2, 3, 4. And we have a chlorine in carbon 6. Go ahead. Here's our substituents. Write a name. Remember, you want to arrange them alphabetically. So chloro will come first, methyl next, then propyl. It's an 8-carbon, so it's a octane, right? It'll be a 6-chloro, 2,2-dimethyl, 4-propyl octane. 6-chloro, 2,2-dimethyl, 4-propyl octane. All right, that's all the rules we have to mess with. Go ahead and name a couple guys. Now our first one, my gosh, I've drawn as a Newman projection, haven't I? Wasn't that mean? Go ahead, untangle this and find the longest chain. Remember, this is the front carbon, big circle is the back. One way to untangle this is to draw it as a sawhorse. Remember, if we do a sawhorse, we just kind of tip it. So this becomes coming towards us, and we can show this one back behind. Here's our front, and here's our back. Now it's much easier, isn't it? Trace out your chain. The longest chain is going to be 1, 2, 3, 4, 5 carbons. So it's a pentane, right? Here at carbon number 1, 2, 3, we have a methyl group. So this is going to be a 3-methyl pentane. There's our chain. Letting that be carbon 1, although I could let this be carbon 1, 2. And it's 3-methyl pentane. Name this guy. Find your longest chain. Doesn't matter which one of these you start with, does it? Longest chain could be that. And it's going to be 1, 2, 3, 4. We're going to let this guy be carbon 1 then. Our first substituents will be here in 2. Write the name. Well, our parent is going to be 4 carbons, so it's a butane. We have 2 methyls, 2,2-dimethyl butane. What if I change this a little bit and I took the hydrogen off and put a chlorine on? Same thing out here. Get rid of the CH2 and put a chlorine. Name this guy. Well, it's still a butane, isn't it? Still have 4 carbons. Now we have to indicate we have chlorines by using chloro. We have 2 of them, so we'll call it a dichloro, right? But where's carbon 1 going to be? Got to be where the chlorine is. That will give us our lowest number here. So we'll let that be our parent now. And we'll let carbon 1 be there. That means we're going to have a chlorine in carbon 1, a chlorine in carbon 3, and we'll have 2 methyls in carbon 2. Write the name. It must be a 1,3-dichloro and a 2,2-dimethyl. 4 carbons, so it's a butane. 1,3-dichloro, 2,2-dimethyl, butane. All right, well, this is really fun, isn't it? Let me show you something amazing that I did. We're back here at the blackboard. See where my little mouse is pointing? It's called Alkane Nomenclature Tutorial. If you click on this, this is what you get. Now, we've seen the JME palette before, haven't we? What you do is, you're going to draw the structure here for 4-methyl octane. Okay. Well, if we go over here, we need 8 carbons in a row. That's our parent. That's 1, 2, 3, 4, 5, 6, 7, 8. On carbon number 4, we have a methyl. 1, 2, 3, 4. All right. I got it right. How about that? Now, if I had done it wrong, it would say, that's wrong. Show answer, and it will show you the correct one. You can also do it backwards. Oh, this is a cute one. 2,5-dimethyl, 3,1-methyl ethyl hexane. That's nice. Here is the other way it works. Very quickly figure out the name for this guy. Our parent is 1, 2, 3, 4, 5, 6, 7. So let's say heptane, right? we have this carbon 1, we have a methyl group here in 2 and 4. So this would be a 2, comma, 4, dash, dimethyl, heptane. I got it right again. Now, there are not an infinite number of these things, but there are hundreds in this little database. So it's a great way to practice. And when you click on Show Answer, you also get a nice abbreviated set of the rules. Okay? Oops. Let's do this backwards and just do a couple very simple problems here. Go ahead and draw the structure of, this could either be 4-isopropyl or 4-1-methylethyl decane. Go ahead and draw these structures and let's see what we got.
Will you be uploading the PowerPoint?
Yeah. Whether it's uploaded, I have to make it available. So, you know, if I ever forget to do something like that, just nag the heck out of me by email, okay? Because I just forget sometimes. All right, for our first one here, we see our parent is a decane. So you want to put 10 carbons in a row, right? On carbon 6, we're going to have a 2-carbon side chain. On carbon 4, we're going to have a 2-carbon side chain with another methyl attached to it. That's the same as isopropyl. This would work. Now, if you drew that on the exam, I would be upset because I have to somehow figure these out. But if you look at it, we can let, this be our longest chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In carbon 4, we have a 2-carbon side chain with a methyl group attached to it. In carbon 6, we have another 2-carbon chain just by itself. 6-ethyl, 4, 1-methylethyl, and it's a decane.
So you prefer us just to make it linear?
Yeah. You know, if you were grading it, would you want to sit there and count out all the carbons? No. Your next one. 2-fluoro, 3-methyl pentane.
This one's
Pentane, 5 carbons in a row. Decide which end you want to make carbon 1. In carbon 2, we're going to stick a fluorine. In carbon 3, we're going to stick a methyl. And that's all you have to it is. Our longest chain, 1, 2, 3, 4, 5. That's carbon 1, so our fluorine is in 2, our methyl is in 3. Our last one, this is a heptane. Hep is 7, remember. So you want 7 carbons in a row. Make one of them carbon 1. Make one in carbon 1. In carbon number 4, you're going to put a dibromoethyl side chain. All right, now let's think about that. You start off with the ethyl side chain, okay? 2 carbons. Carbon 1 is the point of attachment. So carbon 2 is going to be the end. On the end, we have 2 bromines. On carbon 3 and 5, we also have fluorines. All right, 7 carbon chain. This is going to be a 2 carbon chain, and on the second carbon it has 2 bromines. Along our 7 carbon chain, we also have 2 chlorines, 1 at 3 and 1 at 5. Our parent looks like that. We'll let this be carbon 1. At carbons 3 and 5, that's this and this, we have chlorines. On carbon number 4, that's here, we have a 2 carbon side chain. This would be carbon 1, that's carbon 2, and on carbon 2, we have 2 bromines. Any questions? Let's just do one more quick one. Here, just to be silly, I put a molecular model. Go ahead and figure out the molecular model here. Come up with the longest chain. All right, let's see. If we started down here, we would have 1, 2, 3, 4 carbons, right? Started here, we'd have 1, 2, 3, 4. They're equivalent. So we have a 4 carbon parent. It's a butane. We'll let either one of these be carbon 1. Oops. And that means we have a methyl in carbon 2, a methyl in carbon 3, and it is a 2,3-dimethyl butane. Now, as you do your lab report, as you've already seen, you will be using JME to draw structures. You will draw structures of alkanes and branched alkanes. Okay? You will also go backwards. You will be given the structure, depending on your luck of the draw. You'll You'll be given a structure, and you'll convert that structure into a name of some sort. When you type it, please make sure you follow the rules. No spaces, only commas and dashes. All right, you good? All right, there's one more section in chapter 3 that we're actually going to move forward, and we'll do that in the chapter on cycloalkanes. So on Tuesday, remember, we do not have lab. We will have lecture, and it will be chapter 4. And I will do my best to make sure that the mini prints are online.
Don't worry, I'll harass you to put it.
Right. Harass the heck out of it. All right, thank you. Have a good day. Have a good weekend.
That's all.